This is a next tutorial related to electrochemical impedance spectroscopy. In this case, we consider phytosensing part, so how to sense impedances with plant. And in this large problem, we focus today on very dedicated topic of ground and current loops. Shortly to remind, we had already a few tutorials from basics of impedance spectroscopy up to specific points, but they was dedicated to water research. And from this tutorial, we start a new topic that is mostly focused on plants. So for plant research, we are preparing now specific application notes for using phytosensor in precision agriculture, vertical farms, hydroponics. Of course, we'll consider several sensors, among them impedance. And to say generally, this impedance sensing is very similar to impedances. How do we measure them in water? But it still have some specific dedicated aspects. And to understand these aspects, I would recommend to review several papers. For instance, I give some three examples. In internet, of course, you can find a lot of them. So generally, this topic of impedance sensing in plants is now quite popular. Well, to again to remind a little bit some basics of impedance sensing. How do we do this? We create two potentials, high potential and low potential. In plant research, they are inserted in the system by these electrodes, also small silver electrodes. And this differential potential created current, and we are sensing current through this organic tissue. To underline, we have here two very different phenomena. So one is a resistive part, and resistive part typically is related to different ionic effects, ionic flow, intercellular ionic effects, water and similar issues. The second one is a capacitive part. And capacitive part is in charge of absolutely different effects, like the appearance of double electric layer, polarization of electrodes, influence of electrical properties of tissues, and several other properties. So they are really different, and it need to keep in mind always that we are measuring two different phenomena. The point of this tutorial today is basically this ground signal or ground line. Why it's important? Because this, for instance, high potential is related always to the ground signal. So it's, you know, if you have two, for instance, wires, two electrodes, you can think that they are the main wires or main elements in the system. So they created this current. It is correct, but all of them, also both of them, are related to the ground signal. You can think that this element producing this high potential, this is normal power supply unit. You have plus here, minus here, and this ground line work like a minus command, minus for your system. Same way here in the measurement part, this transimpedance amplifier converting current into potential again do this in regard to this ground signal. The point is, if this ground signal is changing, so all this, of course, potential will be changing, and you will see different result in your measurements. Now I try to formulate this a little bit in the terminology of embedded devices. We usually separate between analog ground. That analog ground is this part that generate and sense analog signal. This is extremely important part, because whatever you are sensing in your setup with organic tissues or microorganism or water is generated in analog way. Any mistakes or artifacts created here will be reflected in the all elements of your system. After analog part, typically here you have analog to digital converter. You convert everything to in digital form, save this, store, transmit, and this part has a digital ground. Typically, digital ground has a lot of noise, digital noise, and in the system design we try to separate analog and digital grounds. But in embedded design, I mean, the system is really small. You have only one microcontroller, so you cannot completely separate analog and digital ground. But we still try, I mean, to introduce some filters, some element to decouple both grounds. So after this, of course, you need to power the system. So typically we do this through USB, and here we encounter the next ground is protective ground. Protective ground try only to remove interferences generated here, as it is a long line, to remove these interferences and to put them, for instance, to the earth wires. So from this point of view, this ground should be again separated from analog and digital grounds in your system. But in, let's say, common setup, if you use a personal computer here with ATX power supply, there is a specific element in this in such system that minus of 5 volt is connected to this protective ground, and it is connected again to protective earth wire. It means whatever you sensitive analog ground, I mean, perform all these measurements, this is connected always to this protective earth wire, and this wire extremely noisy. It means if you use this kind of setup, this noise from earth wire, because you know this is a common wire, goes through the whole building. People introduce some other insert devices, remove devices, switch on, switch off, and all of this produce noise, and all this noise goes to your analog ground and to your measurement. So this is one of the source of noise in your system. The second, let's say, even more essential problem appear if you have multiple power supplies in your system. Why? Because, for instance, here you have many embedded devices. You use one common USB hub, and this hub should provide enough current, and so you, I mean, power by independent power supply. So here, as a first point, is already not good because of, I mean, the question is always from which of this power supply the system will be powered. And if, for instance, here is 5 volt and here 5.1 volt, so it still be powered by ATX power supply until it reach our current limit, and then it switch to the secondary power supply. And you know, this switch again produce a noise, and this noise is continuous noise that should be in fact avoided. But a more essential issue is here that this ground here and this ground here is not the same ground. So here you have a long line, it has some resistive part, some inductive part, capacitive part, and so this ground fluctuate in relation to this ground. Essentially, if you in your system have multiple power supplies with common ground, for instance, we in our vertical farm we use a number of 12 volt for water pump, for LED lamps, and of course they also interact with ground in your system. And then what in fact happening? You have here different grounds, and you have a current flowing between different grounds. It means this exactly the name of this issue is ground loops, because exactly of this multiple ground in your system with multiple current power supplies. So one of immediate consequence of this ground loops is a shift of potential. Easy to demonstrate. There is an example. Here we perform this measurement, and here, so here and here I inserted and removed some device from the network, and you immediately see a change of potential. So just to underline, the system works stable. There is no reboot, no stop of measurement. It's just a shift of potential, shift of analog ground, and you see it's look like, you know, you jump in your measurements and another position. If you have a low pass filter here, then it's look like, you know, very smooth change of dynamics. And you can think, okay, I have some event here in my system and I see a reaction of impedance on this event. But in reality, you see only artifact related to a shift of analog ground in your system. So from this point of view, please check always if you observe something like this, remove low pass, and if your dynamic, original dynamic has such form, it means it's definitely an artifact in your measurements. Another essential problem is a noise. Especially this 50 and 60 Hz noise. This appears because of this DC to DC or AC to DC converters. There is no clear separation between AC and DC part, and this current is modulated by noise, by 50 Hz or 60 Hz noise. I show this, so this part has exactly this large amplitude noise, and here you still see here, let's say, different amplitude of digital noise, but this 50 Hz noise is something like factor 10 in amplitude larger than this small digital noise. So this extremely, you know, if you have something like this, in fact, you cannot perform any useful measurements. Last problem that appear, it appear only in seldom cases if one of this power supply is of not good quality. This current is high amplitude. And if you put some additional element that exactly produce this high current, so you can experience, for instance, burnout of some COM port, or you know, you can destroy some element here, or you can destroy USB hubs. In some cases, you see a reboot of devices, or because of this spike of potential. So if you have any of these, let's say, appearances, stop measurement, disassemble your network, and try to debug it and to remove this power supply that has this so undesired effects. Now a question is how to avoid all this problem, and like I said, this issue is well known in the community. Industry already has solutions for this. Most simple solution, try to use USB to USB isolators. They are here, you insert them immediately after USB hub. There are several such devices. For instance, I have some on the table. There's some USB stick, so it's implemented like a stick. This USB hub with 1 to 4 USB hub, also with isolation, or for instance solutions like this. The cost factor is between, I would say, something like 10-50 euros after 50-60 euros. So there's a range of solutions, and implementation is rather trivial. You just insert here after USB. Here is another point. If you would like to have a really clear system without noise, you can replace this power supply. Instead of using AC to DC converter, you can use batteries. So in this case, you remove this noise, and they provide much more clear signal for recording. Here is a specific point. This protective ground. And if you have in your setup some source of alternating magnetic field, they will generate a current in this protective ground wires, and this flow back to your analog ground in the system. How you can see this? If you switch on, for instance, a lamp, so LED lamp, and you immediately see in the signal some modulation or shift of potential, it means you have this kind of phenomena. We also periodically see this elsewhere as well. Try to replace this power supply for this LED light. So it should not happen. In some cases, makes sense, for instance, to cut this protective ground from this point and to connect it to a separated high-quality earth protection wire. So you, in this case, you even improve a quality of your signal. And of course, try to avoid electromagnetic emission in the setup. So this is the first point what I would like to explain here. But in impedance spectroscopy, we have a second point. that is related to current loop in measurements. Again, in impedance, when measuring resistance or impedance, we generate difference in potential. In our case, is alternating signal here. We can use sinusoidal or chaotic signal, depends on what we are going to measure. And it seems here it's only one loop. So by Kirchhoff law, this loop is independent, for instance, of the length of wires, though it's noise immune. So it's a good point. In measurements, we frequently use these current loops for sensing of remote objects because of this noise immunity. And we receive a number of questions regarding this noise immunity. Why, for instance, in some cases it doesn't work. And the point is, again, here we have a capacitive part that work with electrical field. And whatever electrical field the system is surrounding, for instance, here is soil moisture stick, so it also sensing electrical field, it produce electrical field and sense them. And of course, if they are close enough to each other, so this will influence electrical field in this, in vicinity of these electrodes, and you will see interferences between both sticks. The second point, the plant itself has a capacitance because there is a large object, and if I will touch one of these electrodes or some piece of plant, I will add my body capacitance to the plant. And body capacitance has again some common ground, and this common ground will interact with this common ground. From this point of view, I will add here additional loop. It's not only now a single loop like we had before, or in classical case with this current sensing. We have here multiple loops, and in some points we will put additional current or remove some current. This all phenomena that's no longer related to classical case of noise immunity current measurements. From this point of view, please be aware that if you have a capacitive elements, the system will anyway interact with all changes of capacitance in your setup. So even like say it additional sticks or additional technology, or even with a strong electrical field. So some devices they produce electrical field, alternating electrical field, and they of course will then change your system. So again, mostly what we see in Phytosensing, there are AC to DC converters for LED lamps. There is a typical problem what we see a number of cases. So, and one point, do not touch a running setup. Keep setup undisturbed. It's a typical issue. If you are measuring something, even do not enter in this room because plants are sensitive to static electric field. Keep the setup undisturbed. We have one issue that is now related to differential impedance measurements. So question is, well, we have two channels. Typically in one channel we place electrodes in one channel closely to roots, to soil, to measure effect, also phenomena related to soils, and the second channel put more higher position to measure effects related mostly to transpiration, to photosynthesis, to leaves. And we compare both results. The question is whether they are independent from each other. So this was also one of questions what we received. We already answered this in context of water research. Here in the plant is a little bit more complex than in the water research. So here we will consider again resistive part and capacitive part. I prepared a small demonstration here on the table. And we will in fact demonstrate both cases. So this the setup. I have here spectrometer, so blue box. Here is USB hub. So this connected here to USB hub. So I will use for demonstration so these electrodes, because they are more compact, so they're much more easy to handle. Now device is already connected. I start a new data. So here we have a more compact client, is client 1.4. We try to simplify the visual representation, but still the system is fully functional. You here you can enable different apps with different analytic tools. So functionality of version 1.4 is, let's say, it provides the same functionality like all these clients before. Well, now I switch to two-channel representation. As typically you see some noise in both channels. And to demonstrate the first point, the independency of resistive part, what I will do, I will open one and change resistive part of the system. So I will take the channel 1, unscrew it, and what we see a change of impedance to unconnected electrodes. So, and you see here in the first channel, you see change from 200 kilo ohm up to about 1 mega ohm, but there is no changes in the impedance of the second channel. So from this point of view, channels are indeed fully independent. If I screw this again, you see, so I change impedance something like 5 times, and there is no differences in the channel 2. So from this point of view, if I change resistive part of one channel, we do not see any changes in the second channel. So the channels are fully independent. Now, just to demonstrate that the system is operational, I unscrew the second channel. So we have here again open electrodes, and you see that the channel 2 is reacting. So that was real measurements done in this setup. So now I will try to demonstrate the second point. If we have a capacitive change in the setup, what will happen then? For this, I will again unscrew and touch and add my body capacitance to the system. So once again, I start a new data file. Explanation again, what we will see here, my body capacitance has again some virtual ground, because I mean, here in the room there is a lot of electric field, magnetic field, 22 volt wires, and the system now you see is directly connected to USB. So in this setup I have now the issue of this ground loop, what I discussed, so I demonstrated before. So now I unscrew this, and I touch, so I put my body resistance, and you see immediately a reaction of channel 2. You see there's large amplitude signals. Now it start to interact. It's whatever we see immediately a reaction with my body capacitance through this command ground. So you see there is quite well visible, so almost, I mean, in this case we increase the amplitude of the signal, and we see this interaction part and almost no noise, also no changes in the next part of a signal. So to explain what is happening here, we have here the same problem like I discussed before. So my body capacitance is interacting through a common ground. So this virtual common ground, it's still interacting in capacitive way through electric fields, alternating electric fields, still interacting with ATX power supply, and is interacting again with analog ground of this measurement device. So it sounds a little bit crazy, but this is the way how electric fields appear or work in the setup. So here, by touching here, I do not change a measurement. This is important. I do not change a measurement of one channel, but I changing measurement properties of the system. So I'm interacting now with analog ground. So question is how to prevent this phenomena, how avoid this. Like I said before, we try to decouple analog ground. From this point of view, I will use one of these USB. So I will put this stick USB to USB isolation. So stop. So disconnect. So I put here, I connected it, and I connect to, so now it's look like this. So it's connected to USB port. The system work again. And I start measurements. So again, new file, and now I will touch channel 1. I unscrew it, and I touch channel 1, untouch it. So we have modulation of channel 1, red channel by my body. You see this? I will do this a couple of times. And you see more or less modulation of modulation of signal by my body capacitance. In this case, essentially reduce amplitudes of that signals. Here is this setup about 10 minutes later, and you see this part if I touch electrodes with my body capacitance, and this is dynamic after this. So we still hear some spikes, so they are a little bit of more higher amplitude, but generally we do not see any essential differences in this part, and let's say any other parts of this dynamics. Just to conclude, both channels are independent. So for resistive components, for sure, but we still have capacitive phenomena and this capacitive phenomena interact with analog ground. So from this point of view, again, like said before, please be careful of current loop and impedance and capacitive effects. Here, but we have another phenomenon that sometimes can appear. It means this auto-amplification. Auto-amplification measuring ranges, signal range in both channel, and if even one channel is out of range, it amplifies the change amplification factor. But this amplification factor is common for both channel. So from this point of view, it can happen that you change impedance in one channel, auto amplification adapt, and you see a change in another channel. So from this point of view, it's not, let's say, dependency between channel, but this kind of how the system interact with essential changes of impedance in one of channels. So to avoid this, here try to put instead of auto, put to some range that you manually select. So to conclude, just be aware of this ground and current loop in the setup with plant. So plant is a large object that's quite complex, a lot of different capacitive phenomena, and then please think always that you have this effect of current loop through electrical fields. So try to avoid magnetic field emission, especially magnetic field through AC to DC converters or LED lamp, any power supply units. Try to avoid this. So simply use USB to USB isolators. They essentially decrease effect, so they cannot remove it completely. So it's well understandable because they are still connected, but you decrease it by probably factor 5 to 10. So, and use battery for powering. This provides very low noise, and especially important, keep the setup undisturbed. So do not touch running setup. This is common, like I said, because plants are extremely complex and you have a lot of interferences through electric fields. So that is all for this short tutorial. We are preparing next tutorial now that is related mostly to phytosensing. So we will see you in the next video.